Hey students, today we want to talk about exponential functions, so let's get started. I think some of what we talk about today will be review, maybe not all of it though. So let's start off with a positive number. So let's let b be greater than or equal to 0. So the exponential function with base b is, and we'll just write it out, so here it's defined by, so this is defined by the formula f of x equals b raised to the x power. Now, I want to just talk real quick about what this means exactly, right? What does it mean to take a real number and raise it to a power x? Well, it depends on what that choice of x is. So if n is a positive integer, then this formula, so f of n, right, that would mean b raised to the n. And what does that mean? Well, it just means multiply b times itself, right, so n factors. Right, just multiply n, b times itself n times, right? That's what b to the n means. Also, we'll say and if we have a negative integer, so f of minus n, that means, right? So then we've got b raised to the minus n. That just means reciprocal, so it means 1 over b to the n. Also, we can define b to the 0, so when we plug 0 in, right, that's equal to 1. Right? So I think everyone knows this. If we take a rational number, so if, let's say x equals p over q, is rational, meaning that we just got fractions here. We got a fraction, right? So p is an integer and q is an integer. Then f of x, that's going to be b raised to the p over q. And what that means is b so that's equal to b raised to the p, and then you take the qth root of that. And this can be written in either way. It's the same as taking the qth root first and raising it to the pth power. So either of those is fine. So all of these make sense, right? We know what nth root or qth roots are. We know what raising numbers to powers are when we've got an integer. And then the question becomes, okay, what if we take a real number? So if x is irrational, right? We know what it means to do for rational numbers because we understand what's happening when we're talking about integers. So now if we take our irrational number, then there is a sequence of rationals that converges to our irrational number. And so in that case then, we can define what it means to look at b raised to the x in that situation. So in this case, b raised to the x is equal to the limit as r approaches x of b raised to the r, where r is rational. And so this gives us a complete definition of what it means to raise b to various powers, right? And I'm not going to make a big deal out of this at all. Just for consistency, for completeness, right? I want to explain what it means to raise a number to an irrational number also. So now we have a complete understanding of what what it means right? What the exponential function, what it means. Okay, so let's move on. And really, I don't want to make a big thing out of this. The important thing is we want to talk about exponential functions, and I think we all have a good feel for what it means to take a number b and raise it to a power. This just makes it precise. So now graphs, the next thing we want to look at is the graph of an exponential. So graphs of exponentials. And there's really, well, I guess there's three options really. Now the first thing, we know that b to the 0 is always equal to 1. So that means that the graph of an exponential is definitely going to pass through the point 0, 1, meaning this is at height 1 right there on the y-axis. So this is what the graph y equals b to the x looks like in the case that b is strictly greater than 1. Right? It's got this sort of ski jump shape. Here's the graph y equals b to the x in the case that b is between 0 and 1. And then there's sort of the uninteresting case when b equals to 1, we just get this horizontal line. So this is the graph y equals 1 to the x. All right, it's just a horizontal line. So that point right there, I don't want to crowd my picture, but this is at height 1. So that right there, if you can label it, I guess I'll put it right there. All right, that's at height 1. Every exponential function passes through, or every exponential graph passes through the point 0, 1. Right? Why is that? Because b to the 0 is equal to 1. Exponential function has some properties. I think you've probably seen these. You learned these in probably a pre-calculus course. But let's get them all down here. So properties of exponentials. So let's assume b is greater than 0, b not equal to 1. Most authors don't even consider this function 1 to the x to be an exponential function. So typically, you just say, let's not have b equal to 1. Right? 1 to the x is not an exponential function. It's really a linear function. Okay, so the properties that we have are, number 1, when you multiply exponential b to the x times b to the y, where the bases match, you add the exponent. So b to the x times b to the y is equal to b to the x plus y. When you divide, I think everyone knows this, you subtract the exponents. So b to the x divided by b to the y is equal to b to the x minus y. Third property, b to the x raised to the y, that's equal to b to the x times y. Right? So when you exponentiate an exponential, you multiply the exponents. And then the last of the properties, if we have different bases, so let's say a to the x times b to the x, right, you can multiply the bases. This is equal to ab raised to the x. Right? So here's some properties. I believe these are all review for you, but it's just worth having these down. Right? We're going to use these quite a bit. Right. Okay. And then the next thing, these are also properties, but this is limits of exponentials. So same thing, let's let b be greater than 0 and b not equal to 1. Three properties here. The first one, the function f of x equals b to the x, so our exponential function, is continuous with domain. So the domain of the exponential function is all real numbers, so minus infinity to positive infinity. range is 0 to infinity. So, and you can see this from the graph here. I'm about to erase this, but let's take a look, right? So you're allowed to plug in all real numbers. It covers the x-axis, but the output is always greater than 0, right? So the range, right, is 0 to infinity. That means the output is always a number that's strictly greater than 0. Okay, so part 2, and you will be able to see this. I have to erase the graphs here, but you'll be able to see this. You can see this from the graphs. So if b is greater than 1, then the limit as x goes to infinity of b to the x is equal to infinity, and the limit as x goes to minus infinity of b to the x is equal to 0. So that means that we've got a horizontal asymptote. And then the third property, if we have b between 0 and 1, then the limit as x goes to infinity of b to the x equals 0. So once again, we've got a horizontal asymptote. In both of these cases, the x-axis is a horizontal asymptote. And limit as x goes to minus infinity of b to the x is equal to positive infinity. You'll need these limits. These are things that you need to understand. I guess I would say memorize them, but memorize them by understanding the shapes or knowing the shapes of the graphs of these functions. Okay, so we've got properties of exponentials, we've got limits of exponentials. Now we want to do the derivatives of exponentials. So same setup. Let's let b be a positive number with b not equal to 1. And let's write this out. So let's say, and let f of x be the exponential function with base b, so that'll be f of x equals b to the x. All right, so what I'd like to do is compute f prime. So then, and I'm just going to use the definition of the derivative. F prime of x, by definition, that's the limit as h goes to 0 of b to the x plus h minus b to the x all divided by h. This is straight from the definition of the derivative of a function. And I want to do a little bit of simplification here. So I'd like to factor a b to the x out of each piece in the numerator. So this will be a limit as h goes to 0 of b to the x times b to the h minus 1 all over h. And I'm going to continue with this, this equality here. So that's equal to limit as h goes to 0 of b to the x times b to the h minus 1 all over h. And that piece in parentheses right there, that fraction in parentheses, should look familiar. This, and let me write it out one more step here. So this is the limit as h goes to 0 of b to the x times b to the h plus 0 minus b to the 0 divided by h. Hopefully writing it out that way makes it look a little more familiar. This right here is the derivative of the function at 0. And so what we get is b to the x times f prime of 0. This is an incomplete formula, but for now let's just write this down. So what we showed is that f prime of x is equal to f prime of 0 times b to the x. So we're not done, but there it is. All right, we'll need to elaborate on this, and especially what we'll need to do is we'll need to figure out what is f prime of 0. Right? If you have a particular exponential function b raised to the x, what is this? Right? So what this is saying, though, is that the derivative of the exponential function is a constant multiple of that same exponential function. And who is the constant? It's f prime of 0, which is the slope of the function at 0. So in fact, let's sort of highlight that, right? That's the slope of the graph y equals b to the x at x equals 0. Now, let's just draw, I want to draw out a couple of the graphs for a couple of particular choices of b. So first, if b equals 2, what we get, let's say we've got y equals 2 to the x, right? The graph is going to look like this, and you can actually verify if you look at the slope of the tangent line at x equals 0. It turns out, so the slope is about 0.69. Right? So for y equals 2 to the x, the slope at x equals 0 is about 0.69. If we move over to the graph, so if we let b equal 3 now, so this is the graph y equals 3 to the x, it turns out that the slope here, it's about 1.1. All right, so when b equals 2, slope is 0.69. It gets a little steeper when b equals 3, we get 1.1. So what? All right, so as we look at choices of b, starting at 2 and going to 3, right? It starts at 0.69, it increases. This slope right here keeps increasing. By the time you get to 3, you're at 1.1. And so, there exists a number, and it's going to be some number between 2 and 3. We need to have a good name for this number. Some number between 2 and 3, such that the slope is exactly equal to 1, right? We start at 0.69, the slope increases. Somewhere in between 2 and 3, there's a number that gives us a slope equal to 1. And a good choice for that number is the letter E, right? So there exists a number E between 2 and 3, such that the slope to the graph y equals e to the x is 1. Right? So this gives us a definition. This is how the number e is defined. Right? So definition, e is the real number such that, so let's see, how do you compute the slope at 0? It's the limit such that, let's say like this, e equals the limit as h goes to 0 of e to the h minus 1 divided by h. So here's our definition of this strange number e, right? I'm sure you've seen this number e. Here's what it is, right? It's the number that makes the slope of the tangent line equal to 1 when x equals 0. Okay, now I've just erased that formula. F prime of x equals f prime of 0 times b to the x. Well, in the special case that we're working with e as our base, All right, so what do we get then? We get the derivative of e to the x. Well, let's see, it would be the derivative at 0 times e to the x. We know the derivative is equal to 1. And so this gives us the easiest derivative formula in calculus. The derivative of e to the x is equal to e to the x. On a test or a quiz, you're never going to get a problem that says compute the derivative of e to the x. But what you will get is problems that ask you to use this formula in conjunction with a chain rule. And so what we need is a more general formula that tells us how to compute the derivative of e to the f of x in the case that f is a differentiable function. And the chain rule tells us that it will be f prime of x times e to the f of x. That's the formula that you need. Right? This formula you'll definitely need to see. So for example, the derivative of e raised to the sine x, take the derivative of the exponent function, the function up there, so that'll be a cosine of x, and then you follow it by e to the sine of x. So this is the formula. I mean, of course you need to know this, but this is the one that you're going to have to use in actual settings on a quiz or a test. Now, every time you get a derivative formula, there's a corresponding antiderivative formula. So let's just say also, let's see, well, what's the antiderivative of e to the x going to be? Well, it's going to be e to the x, don't forget your plus c, right? So the easiest antiderivative formula out there, the antiderivative of e to the x is just e to the x plus c. So for example, let's compute the antiderivative of, how about x cubed e raised to the x to the 4th dx. Well, hopefully the obvious choice here, u equals x to the 4th, in which case du is going to be a 4x cubed dx. If you solve for dx, you get dx equals du over 4x cubed. And so this original integral is going to be, what do we get? A 1/4 integral e to the u du, which is a 1/4 e to the u plus c according to our formula here. And when we substitute back, we get a 1/4 e to the x to the 4th plus c. Okay, so that's enough for today, and we'll see you next time.